Something strange happens when you look at the universe. You probably don't notice it at first. You look at the stars, the planets, the trees, the sky, and you think, this is it. This is reality. This is the universe. But here's the strange part. The moment you try to understand the universe, not just look at it, but understand it, you realize that what you're seeing is not the full picture. The universe is not the way you imagine it to be. It's not what your senses tell you. It's not even what your brain has built from all of that sensory information. The universe is a complex web of forces and interactions. It's filled with mysteries that we don't fully understand, even though we think we do. And the strangest thing about it is this: the more you look, the stranger it gets. You look at the sky and you see stars. You see planets. You see the beauty of nature. You see your own reflection in the mirror. It all seems so real. But when you dig deeper, you realize that none of it is as it seems. Take light, for example. Light is the primary way we experience the universe. You look at something, and the light from that object hits your eyes. You see the color, the shape, the details. Light is everywhere. It's essential to your experience of the world. But the more you study light, the stranger it becomes. Light travels through space at a constant speed, but it's not as simple as that. The speed of light is not a constant in every context. It changes depending on how fast you're moving and how much gravity is around you. If you were traveling near the speed of light, time would seem to slow down for you relative to someone who is standing still. This is a fundamental principle of Einstein's theory of relativity. Light isn't just something that travels through space. It interacts with space itself. It bends, it shifts, and it behaves in ways that we can't easily predict. What seems like a simple thing, the speed of light, turns out to be a much more complicated and mysterious concept than we originally thought. And that's just the beginning. You think you understand gravity. You think gravity is just the force that pulls things toward the earth. You drop something, and it falls. Simple. But again, things aren't as simple as they seem. In reality, gravity is not a force in the traditional sense. It's the bending of space-time itself. The more massive an object is, the more it warps the space around it. This warping causes objects to move toward each other. What you experience as falling is actually the result of the way space-time is curved by the presence of mass. And the more you learn, the stranger things get. You've heard about quantum mechanics, the study of the smallest particles in the universe. You've heard that particles can be in two places at once. You've heard that particles can talk to each other even when they are light years apart. You've heard about the uncertainty principle, which says that you can never know both the position and the velocity of a particle with complete certainty. This is where things get really strange, because quantum mechanics tells us that the universe at its most fundamental level doesn't behave the way we think it should. Particles don't have definite positions or speeds. They exist in a cloud of probabilities until they are measured. When you measure a particle's position, it decides where it is. But until then, it's not really anywhere at all. This is a bizarre idea. It goes against everything you know about how objects behave. You're used to seeing things that are solid and definite. You're used to knowing exactly where something is. But quantum mechanics shows us that reality is not as simple as it seems. And here's where Feynman's genius shines. Richard Feynman, one of the most brilliant physicists of the 20th century, said something that completely changed the way we think about the universe. He said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Feynman understood that the universe at its core is strange. It's unpredictable. It's counterintuitive. And the more we learn about it, the more we realize that our everyday ideas of reality don't apply. The universe doesn't follow the rules we think it should. It's not simple. It's not orderly. It's a vast, chaotic web of particles, waves, and forces, all interacting in ways that we can't fully understand. So, what's really going on? What's the universe really like? That's the million-dollar question. The answer is simple. We don't know. Not yet. And the more we discover, the more we realize how little we actually understand. We are only beginning to scratch the surface. The universe is strange. It's complex. And the deeper we look, the stranger it gets. But that's also what makes it so fascinating. Because every time we uncover a new layer of the universe, we are faced with new mysteries, new questions, and new ideas that challenge everything we thought we knew. This is the beauty of science. It doesn't just give you answers. It gives you more questions. And those questions lead you down deeper paths, to greater understandings, to more profound insights. The universe is not what we think it is. It's not what we see. It's not even what we measure. It's something far deeper, far more mysterious, and far more beautiful than we can imagine. Once you start to see the universe this way, you begin to understand that our human perception of reality is incredibly limited. We rely on our senses, which evolved for our survival, but those senses don't give us a true, unfiltered view of the universe. They give us a version, a useful version, but still a version shaped by biology and evolution. Your eyes see only a small sliver of the electromagnetic spectrum. Your ears only pick up certain frequencies of sound. Your sense of touch is attuned to the surfaces you interact with, but it can't detect the vast range of forces that govern the universe, like gravity or electromagnetic fields. Even our sense of time is limited. We experience it as a steady, unchanging flow, but in reality, time is anything but uniform. It bends and stretches depending on your speed and your location in space-time. This is a profound realization. What we perceive as reality is just a narrow slice of what is actually out there. For example, think about gravity. You experience gravity constantly, right? You feel the weight of your body, the way objects fall when you drop them. You know gravity exists, and you have an intuitive understanding of how it works. Things fall toward the earth because the earth pulls them. But gravity is not as simple as it seems. Gravity is not just a force pulling objects down. It's a curvature of space-time. This idea, developed by Einstein, fundamentally changed how we understand gravity. Instead of thinking of gravity as a force pulling objects, we now think of it as the result of mass bending the fabric of space-time. The more massive an object is, the more it warps space-time around it, and objects move along the curves in that fabric. This is mind-boggling because it means that gravity isn't a force in the traditional sense at all. It's a geometric property of space and time, and it affects how objects move through space. The Earth is not pulling you down with a force. It's causing a curvature in space-time that makes you move toward the Earth. And because space-time is not a static thing, gravity can change. It can bend, warp, and even stretch depending on the mass and energy of the objects around it. And yet, you don't feel any of this when you walk across the room. To your senses, gravity is just a constant force pulling everything downward. But in reality, gravity is a much deeper, more complex phenomenon that stretches across the fabric of the universe, affecting everything from the tiniest particles to the largest galaxies. The same concept applies to time. You feel time as a steady flow, moving from the past to the future. You measure it with clocks, and you plan your life around it. But time is not as constant as you think. It's relative. It changes depending on how fast you're moving and how much mass is nearby. This is another concept introduced by Einstein's theory of relativity. Time does not move at the same rate everywhere. The faster you move through space, the slower time moves for you relative to someone who is standing still. This is known as time dilation. So if you were traveling in a spaceship near the speed of light, you would age more slowly compared to someone on Earth. To you, it would feel like time was passing normally. But to someone on Earth, years might pass in the time it takes you to experience just a few hours or days. This is a radical departure from how we normally think about time. We think of time as a universal clock that ticks at the same rate for everyone, everywhere. But in reality, time is fluid. It bends and stretches depending on your velocity and the gravitational field you're in. And this is not some abstract concept. It's been experimentally verified in particle accelerators, where particles moving close to the speed of light experience time differently than particles at rest. So, you're not just walking through time as if it's a constant, unchanging backdrop. You're moving through time as part of a dynamic process, shaped by the forces and the geometry of space-time. Time and space are interconnected. They are two sides of the same coin, and the way they interact shapes everything in the universe. Now let's turn to light. You probably think you understand light. You see it every day. It illuminates the world around you. It lets you see color, brightness, shadows, and shape. But light is not as simple as it seems. In fact, light is one of the most fascinating and strange phenomena in the universe. Light is made up of particles called photons, but it also behaves like a wave. This dual nature, particle and wave, is known as the wave-particle duality, and it is one of the cornerstones of quantum mechanics. Light is neither purely a particle nor purely a wave. It's both, depending on how you look at it. When light travels through space, it behaves like a wave, spreading out in all directions. But when it interacts with matter, it behaves like a particle, transferring energy in discrete amounts. This is what gives rise to phenomena like the photoelectric effect, where light can knock electrons off atoms. The energy of the light is transferred in discrete packets, or quanta, and that energy is used to free the electrons from the atoms. This wave-particle duality is something that our classical intuition struggles with. We want to think of light as either a wave or a particle, but the universe doesn't care about our neat categories. It behaves in a way that is much more complex and strange. And the same is true for other particles. Electrons, for example, can behave like particles in some experiments, and like waves in others. This is where quantum mechanics begins to blow our minds. In the quantum world, particles don't have definite positions or velocities until they are measured. They exist in a state of probabilities, where they can be in multiple places at once. The Heisenberg uncertainty principle tells us that we can never know both the position and the velocity of a particle with absolute certainty. The more precisely we know one, the less precisely we can know the other. This is not just a limitation of our measurement tools, it's a fundamental feature of the universe. At the smallest scales, the universe is not deterministic. It is probabilistic. And this means that, at its core, the universe doesn't behave in the way our everyday experiences suggest. It's strange, it's unpredictable, and it's far more complex than we can imagine. As we dive deeper into the strange nature of the universe, we start to realize something even more fundamental. Reality itself does not follow the rules of our everyday experience. Our senses, our understanding of space, time, and matter are all based on a very narrow slice of what actually exists. You're used to thinking of the world as consisting of solid objects, fixed locations, and definite moments in time, but when you examine the universe on a microscopic scale, that picture begins to fall apart. Take atoms, for example. Atoms make up everything around you, and yet atoms are mostly empty space. The nucleus of an atom is tiny compared to the space around it. Most of the atom is a vast emptiness, filled with electrons moving rapidly in specific orbits. Yet, even though atoms are mostly empty, the forces at play, particularly the electromagnetic forces between the nucleus and the electrons, are powerful enough to hold everything together. This is where things get strange. The electrons in an atom don't follow the simple laws of classical physics. They don't orbit the nucleus in neat, predictable paths like planets orbiting the sun. Instead, they exist in clouds of probability, where their exact location is unknown. This uncertainty is a central tenet of quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales. Quantum mechanics tells us that particles can exist in multiple states at once. An electron, for instance, can be in several locations at the same time, only deciding on one specific location when it is observed. This is known as superposition. The very act of measurement forces the system to collapse into one of its possible states. But until then, it exists in all states simultaneously. This uncertainty is not just a result of measurement limitations. It is an inherent part of how the universe works. The Heisenberg uncertainty principle states that we can never know both the position and the momentum of a particle with absolute precision. The more accurately we measure one, the less accurately we can measure the other. This uncertainty is not a flaw in our measurement tools. It is a fundamental feature of reality at the quantum level. This leads us to another strange concept: entanglement. When two particles become entangled, their properties become linked, no matter how far apart they are. This means that when you measure one particle, the state of the other particle is instantly determined, even if they are light years apart. This phenomenon defies our intuitive understanding of space and time. It suggests that the universe is much more interconnected than we realize, and that information can travel between particles instantaneously without any regard for the limitations of space or time. These concepts, superposition, uncertainty, and entanglement, show us that reality at the quantum level is not as straightforward as it seems. The universe is full of strange, invisible connections that we cannot directly observe. The particles that make up everything in the universe are not isolated objects. They are part of a web of relationships that stretch across time and space. The universe is interconnected, and the rules that govern it are not as simple as we once thought. This leads us to a profound realization. The universe is not the way we perceive it. Our senses are not equipped to fully grasp the complexity of reality. We see a limited version of the universe, one shaped by our biology and our survival needs. We perceive a world of solid objects and stable events, but at its core, the universe is fluid, probabilistic, and interconnected. And this is where Feynman's insight becomes so important. He was one of the first to truly grasp the weirdness of the quantum world and to communicate it in a way that made it accessible. He didn't try to simplify the universe or make it fit into neat, tidy boxes. Instead, he embraced the strangeness and complexity of the universe, and he encouraged us to do the same. Feynman famously said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." This statement was not meant to be a joke, it was a challenge. Feynman knew that quantum mechanics is counterintuitive, that it defies our everyday understanding of the world. But he also knew that the true beauty of the universe lies in its complexity and its unpredictability. The universe is not as it seems. It's not a collection of solid objects, definite locations, and fixed moments in time. It's a dynamic, ever-changing web of relationships, forces, and probabilities. And the more we learn about it, the more we realize how little we actually understand. This is the most profound insight that Feynman uncovered. The universe is not a simple, mechanical machine. It's a complex, probabilistic system where particles interact in ways we can't directly perceive. The more we try to understand it, the more we uncover new layers of mystery. The beauty of science is that it doesn't just give us answers, it gives us more questions. Every discovery leads to new questions, new mysteries, new frontiers to explore. And the more we learn, the more we realize that the universe is far stranger and more intricate than we ever imagined. As we dig deeper into the universe's strange behavior, we start to confront the limitations of our perception and the very way we think about reality. The truth is, our understanding of the universe is built on a foundation that is at once useful and deeply flawed. Our senses, though extraordinary in their capacity to help us navigate the world, are not designed to grasp the true nature of space, time, and the forces that govern the cosmos. Take space itself, for example. You experience space as something vast and three-dimensional. You move through it effortlessly, navigating from one location to another with relative ease. It feels like a vast, empty container that holds everything we see and interact with. But in reality, space is not empty. Space is not just a backdrop against which objects are arranged. It is an active, dynamic force in its own right. It can stretch, bend, and warp. It responds to the presence of mass and energy, curving in ways that influence the behavior of everything within it. This is where Einstein's theory of relativity fundamentally changed our understanding. Space and time are not separate, rigid entities. They are intertwined in what we now call space-time. This means that the geometry of space is not fixed. It can bend and stretch depending on the distribution of mass and energy in the universe. The fact that space can bend might sound abstract or confusing, but the effects of this bending are very real. A black hole, for instance, is a region of space where the curvature becomes so intense that nothing, not even light, can escape. A black hole is not a hole in space in the traditional sense, but rather a region where the fabric of space-time itself is so stretched that it creates a singularity, an infinitely dense point where the laws of physics as we know them break down. This idea of space bending and warping challenges everything you thought you knew about how the universe operates. You may think of space as a flat, static expanse, but in reality, it is flexible. And this flexibility is not just a theoretical concept, it has real, measurable consequences. For example, time runs more slowly the closer you are to a massive object, like a planet or a star. This effect, called gravitational time dilation, has been measured with extreme precision, confirming that time is not the constant, uniform flow that we experience in our everyday lives. Time is flexible. It stretches and contracts depending on where you are in space-time. Now let's talk about light. You see light, and you use it to navigate the world. Light allows you to see objects, colors, shapes, and distances. But light is not as simple as it seems. Light behaves both as a particle and as a wave. This is known as wave-particle duality, and it's one of the most mind-bending aspects of quantum mechanics. When you look at light, you might think it travels in a straight line from one point to another, and most of the time it does. But when you look closely at how light interacts with matter, you start to see that it can also behave like a wave. It can interfere with itself, creating patterns of constructive and destructive interference, much like the ripples on a pond when you throw a stone in the water. This wave-like behavior of light becomes even more pronounced when you consider phenomena like diffraction and interference. Light can pass through small slits and create patterns that suggest it is behaving like a wave, spreading out and interacting with itself. But when you measure it at a single point, it behaves like a particle, transferring energy in discrete packets called photons. The behavior of light cannot be fully explained by either a particle model or a wave model alone. It has both characteristics depending on how you observe it. This duality of light, acting as both a wave and a particle, suggests that reality is not as straightforward as we assume. The universe is not composed of simple objects and clear-cut behaviors. Instead, it is a complex, multi-layered web of interactions that can appear different depending on the perspective you take. The same applies to particles. Electrons, for instance, can act like particles in some experiments, and like waves in others. This is where quantum mechanics takes us into truly uncharted territory. Quantum mechanics tells us that particles don't have definite properties, like position or momentum, until we measure them. Until that point, they exist in a superposition of all possible states. This means that a particle can be in multiple places at once, or have multiple properties simultaneously, until it is observed. The very act of measurement causes the system to collapse into one specific state. This concept of superposition is deeply unsettling because it challenges our basic understanding of reality. How can a particle be in two places at once? How can it have multiple properties simultaneously? The answer, according to quantum mechanics, is that the universe operates on a level that is fundamentally probabilistic, not deterministic. The behavior of particles is governed by probabilities, not certainties. This is not just a theoretical abstraction. Quantum mechanics has been experimentally verified countless times. The predictions it makes about the behavior of particles are incredibly accurate, even if they seem strange and counterintuitive, and the implications of quantum mechanics extend far beyond the microscopic world. In fact, the technologies that have shaped the modern world, such as computers, lasers, and semiconductors, are all based on the principles of quantum mechanics. But despite its successes, quantum mechanics is still a mystery. It doesn't fit with our everyday experience of the world. It doesn't follow the rules we are used to. And that's what makes it so fascinating. It forces us to confront the limits of our understanding and to embrace a universe that is far stranger and more complex than we could have imagined. So, is the universe really as we see it? The answer, as Feynman would say, is both yes and no. What we see is a version of the universe, filtered through the lens of our senses and our biology. It's a model of reality that works for us in our daily lives. But it is not the whole story. The universe is far more complex, far stranger, and far more beautiful than we can perceive. The more we learn about it, the more we realize how little we understand. The beauty of science is that it doesn't just give us answers. It gives us more questions. And the more we learn, the deeper the mysteries become. The universe is not what we thought it was. It is not what we see with our eyes or measure with our instruments. It is something far more profound, far more intricate, and far more interconnected than we could have ever imagined. Comment below, what part of the universe do you still find most mysterious? I read every thoughtful response. Subscribe for more videos that uncover the deeper truths of the cosmos.